Good day, Vitsies. My name is Dr. Jacques Duplessis, and today I am going to teach you some very, very interesting mathematics regarding limits. We've had quite a few videos in the series, and I hope you watched them so that this one will make just as much sense. Today we're focusing on the Sandwich Theorem, sometimes also called the pinching theorem or the squeeze theorem. Let's not waste any time. Let's get into what we're supposed to do today. Before we look at what the theorem says, we just have to remind ourselves what a limit is and when that limit exists. And I've written it down here for us. The limit when x approaches a of some function f of x will be a value L, if and only if the limit when x approaches a from the right of f of x takes on the value of L, and that is also the same, that this will also be the same when x approaches a from the left of f of x. So that means some value of x, we're going as x is approaching a from both sides, the two limits are approaching the same value. It's not doing this, okay, because that's a discontinuity. Okay, so it's going to the same point. So that's for the limit to exist. Okay, let's see what the Sandwich Theorem actually then says. The Sandwich Theorem says, suppose that we have functions g of x, f of x and h of x, and the functions are such that, now remember, before I read that out, g of x is what the name of the function is. But the moment I substitute a value in there and I talk about g of a or g of b, I'm talking about a y value. So don't forget that. Okay, so what is this saying? It's saying g of x, the function, is smaller than f of x, so it lies below f of x, and then f of x in turn lies below h of x for a particular interval around a point C. Okay, so this is indeed, if I draw this for you, the function that would lie at the top is the function h of x. So let's draw any function. Let's just go like that. There's my h of x. Okay. Then I have f of x, the second function. So this is where f of x might lie, for instance. And then I have the function that lies right below here. Now, what the pinching theorem is saying, or the squeeze theorem or the sandwich theorem, whichever one you want to use, we are focusing in here at around C. So this is the area where we are focusing in on. That's where x is becoming equal to C. Now what does it say? It says the limit when x approaches C of g of x here takes on the value L, and so does the limit of h of x. So the bottom function and the top function's limits are the same when x is approaching the value C. And that value is over here, that value is L. It's approaching the value of L. Well, this theorem says if that is the case, then the limit of the function f of x will definitely also be L, because it's lying between h and g. So h and g is coming closer to the point. This is what's happening, is going closer to the point, and somewhere in the middle here is where f of x is running. And it's saying that if that's the case, then the limit of the middle function will definitely be the same. So these two outside functions are squeezing the inside function, so you can see where the name comes from. Or it's sandwiching them. There, piece of bread, something in the middle. And that's the f of x. Okay. Very important theorem, folks. Very difficult sometimes to apply, but I'm going to try and do my best to make it as easy as possible for you. What are we doing if we apply the squeezing theorem? That's what I want to look at. When trying to find a function to squeeze, and in this case, if I just bring my previous paper back, the function that we wanted to squeeze was f. We are looking for other functions that are similar enough to f. Now I can imagine they have to be around this area here. They have to be, and we call it x approaches a there. As it around this area, the behavior should be the same. The behavior will only be the same if there's similar functions around that f of x that behaves in the same way at the point. Then the limit, the y values will be the same. Okay, so that's what we're looking for. We're looking for similar enough functions to the function that lies in the middle. This I wrote f of x, g of x, that's supposed to be f of x, sorry. Okay, and we need to make sure that it works. The squeeze works, and that's why we want similar functions. And then also, functions that are easier to evaluate in the limit than the function that we might necessarily be looking at. Okay, so to demonstrate this to you, I'm going to do an ugly one. Let's start with a limit when x approaches 0 of the function x squared cosine 1 over x squared. Now remember, at school you worked in degrees when you worked with trigonometry. At university, we work in radians. Okay, so this x represents that. Okay, folks, so yeah, now what do we do? Let's see. We choose, first of all, the function here that has the most complications for us and that we know something about. Okay? Now, in this case, I think it's the function, the cosine of 1 over x squared. Why am I saying that? Because we know from school maths again that the cosine of an angle will never be higher than 1 or lower than -1. I'm not talking about 3 times that cosine. I'm talking about the cosine of theta. Remind yourself, the cos of theta lies between 1 and -1. Now that's how we write it at university. Unfortunately, at school you didn't learn about absolute values. So I'm just going to take it one step further. This is what you learned at school. Cos is below 1 and bigger than -1. These two things mean exactly the same thing. So if you see that in a textbook, that is what it is representing. Okay, so I'm going to start with that. I'm going to look at what happens with a cosine of 1 over x squared. Now, I don't care what this angle is. I'm not interested in that. I'm just seeing it as an angle. I'm definitely sure that that would lie between 1 and -1, and that comes directly from your school mathematics. But this will only be true then here for x's that are not 0. Because if my x is in the denominator, I'm creating a little problem for myself. Okay, now let's have a look. If I now have to, remember what am I doing now? I'm starting with the most complicated part, which was that part. And I now need to bring in the rest, because I can't just look at this. I need to bring in the x squared. And what is it in the original sum? It is multiplied to this. Okay, so I need to look and zoom in on what x squared does. So I say to myself, what do I know about x squared? Well, at school, I learned that anything that is squared is always bigger or equal to 0. It's a positive number. That's what it's saying. If we're excluding x, so we will know that x squared will be strictly positive. It won't become 0 anyway, and it won't become negative. Now, Vitsies, why is that important? If I multiply over an inequality sign with a negative, the sign changes direction. So in other words, if I multiply this with -3, these signs have to face the other way because I multiplied with a negative. So I must make sure that what I'm multiplying with is a positive. And now I'm going to do it. I'm going to multiply with x squared because I'm sure it's always positive. So then I'm creating minus x squared. I'm multiplying it over here. Okay? Is less than equal to x squared. the cosine of 1 over x squared stays, and that will be smaller and equal to x squared. And look at what we created. We found the two functions that will squeeze the function that we started with. The two functions that squeezes it are those two on the outside. I'm going to underline them in red because now we're going to zoom in on their behavior. Why? Look at our diagram again. We found those two in this case. Okay, they are going to squeeze the initial function at the particular point that I'm looking at. And that's what I'm interested in, because the one on the left and the one on the right are going to behave the same way when I let x equal 0. Okay, so now we look at that component. We say to ourselves, what happens if I take the limit when x approaches 0 of the number minus x squared? Well, I think it's quite straightforward. There's no problem here. There's no form 0 over 0 or infinity over infinity. There's no number over 0. There's no number over infinity. It's a plain, straightforward substitution. X becomes 0, so minus 0 squared is still 0. Okay? And the same is true for the limit when x is approaching 0 of this x squared. Now, folks, I think if we look at what the theorem said, look at it. It says if the top and the bottom goes to the same, the middle will also go to the same value. So we can say now, by the, I'm going to write Sandwich Theorem as ST. You must please write it out. By the Sandwich Theorem, the limit when x approaches 0 of x squared cosine 1 over x squared will then also be equal to 0. So it's not a difficult idea, but the application becomes difficult because it depends on the complexity of the function that you're going to work with. Okay, let's look at some other ones that are just as interesting as the one that I just did for you. The one that I'm going to look at now also has some complexity in it. In this case, we're going to work with a natural base. So we're working with a limit when x approaches 0 of x squared multiplied by e. Now look at how ugly I'm going to become. I'm going to say in the power the sine of 1 over x. Now that in itself looks very intimidating. I mean, if I look at this, it makes me worry. So what do we need to choose? We need to choose the most complicated part of what this function is. And for me, again, it is what I know. I know the sin of theta. Remind yourself, the sine of theta at school level was between 1 and minus 1. Nothing has changed at university, and nothing will ever change. It will always be like that, unless you put a number in front. Then it changes, because then you have to do the same to both the other sides. So that's what I'm going to start with. I'm going to say, you know what? I know the sine of 1 over x lies between 1 and between the minus 1. And this is true for all the x's that are not equal to 0. Again, I need to remind myself that x is in a denominator. Okay, but that's not what this looks like. I now need to take this and I need to get it into some power. And e is what I need to focus on. So I say to myself, but what is e? What is this value of e? And I know e is 2,718, and there's quite a few more decimals. The point I'm making is that e is positive. Okay, so this is bigger than 0. Now, very interesting here would be for myself now, what do I do to get that into the power? Well, it is positive, so it does not change anything that is written down about the sine of 1 over x. Okay, so I can immediately raise everything to that power. So I say e to the power minus 1. I need to get it back into the power. is less than equal to e to the power sine 1 over x, which is less than equal to e to the power of 1. And remember, the restriction still applies. Okay, so I now have this part is now back into the picture. I now need to, as I did before, discuss the x squared. Well, I know that x squared is bigger or equal to 0 for all x's. Okay, so what can I say? If I exclude 0, then x squared will be positive for all x values that are not 0. It won't be equal to 0, but it will be strictly positive. So what can I do now? I can now multiply it in across all three of those. So I'm sitting with x squared multiplied by e to the minus 1 is less than equal to x squared multiplied by e sine 1 over x is less than equal to x squared e to the power of 1. So what did I just found out? I found out that my function in the middle is being squeezed by those two on the outside. The one lies at the bottom, the other one lies at the top. Okay, and the only difference is that I've got e to the minus 1 and there I've got e to the 1. So I need to zoom in on these. Those are the two important ones. So what will the limit be when x approaches 0 of x squared e to the minus 1? Now, e is that number. It's a constant. It's a number. X becomes 0. 0 times anything is 0. No change away from that. And the same for this side. This will be equal to the limit when x approaches 0 of x squared times e to the 1. 0 times anything is 0. So by the Sandwich Theorem, I can say that the limit when x approaches 0 of x squared e sine 1 over x, that limit is 0, folks. It's poetry. It's absolute poetry. I love the Sandwich Theorem. You just have to really think very carefully where you start. And you've got to start with the function or the part of this function that has the most complication for you. Okay, let's look at one that is slightly more complicated than the one that we just looked at. Not really that much more complicated, but yeah, we're going to look at the limit when x is approaching, look at this now, infinity of x minus 4 sine x over 2x. Okay, that's interesting. Now remember, please, Vitsies, you cannot say that x cancels with that x and this x over here. This x is protected by a ratio. I call the ratio the bodyguard of the angle. You cannot get to the angle unless you get rid of the bodyguard, and in this case you can't. The second thing that you're not supposed to do is to say that 2 goes into 4 twice, because you then have to divide the 2 into the x as well, and you can't. There's nothing to divide there. So please don't do silly things like that. Just remind yourself of the absolute basics. Now I can hear you guys all shouting to me that I'm going to start with a sine of x. And that is definitely what we're going to start with. We're going to acknowledge that we know that the sine of x lies between 1 and definitely between minus 1. But now look at the interesting part. I am now going to multiply with a minus 4 because I need to form minus 4 sine x. So the moment I times with a minus 4, my signs will all change direction. So a minus 4, let me write it in red here, I'm timesing here with minus 4, timesing there with minus 4, and I'm timesing that with minus 4. Once I do that, this becomes a positive 4. The signs change direction because I'm multiplying with a negative over an inequation, okay, or an inequality. Fine, so this becomes minus 4 sine x. So I'm moving closer to what I had, and this is then bigger than minus 4. Okay, what do I need to do now? Well, it looks like I need to add x. So in my next step, I will be adding my x, and then nothing is going to change. Why not? Remember, x is approaching infinity. Okay, so it's going to a large positive number, so this is still positive. So x plus 4 is bigger than equal to x minus 4 sine x, bigger than equal to x minus 4. I'm almost there. I now have formed the numerator. So far, the numerator is being squeezed by those two. I now need to divide by 2x. And again, because I'm going towards positive infinity, if I divide by 2x, 2 is positive, x is positive, so the 2 does not change anything. So I can say x plus 4 over 2x is larger or equal to x minus 4 sine x over 2x, which is in turn bigger and equal to x minus 4 over 2x. Okay, quite neatly done. I now only need to focus on the two outside functions that is squeezing the inside. And folks, you can see they're easier. They're much easier to find the limit of than what the original was, and that is the point. Okay, so we say the limit when x approaches infinity of x plus 4 over 2x. Remind yourself again that this is the principle. I've got 1 over x. If x approaches infinity, 1 over x approaches 0. And that's what I want to apply over here. So what am I going to do? I'm going to multiply the top with 1 over x. So in other words, I'm dividing everything there with x. And I do the same with the bottom. Why do I need to do the same? Because I need to multiply with 1 so that I don't change the value of what I had initially. Okay, so that becomes the limit when x approaches infinity. I have x times 1 over x is 1 plus 4 over x. Bottom simply becomes 2. Now look at the beauty here. I'm applying this rule, so I've got 1 plus 0 over 2, and that leaves me with a quite comfortable 1 over 2. Now folks, if you look at the same is going to happen here. The limit when x approaches infinity of x minus 4 over 2x, everything is the same, except for that's a minus there, and that's a plus. So this, in the same way, is going to become the limit when x approaches infinity of 1 minus 4 over x over 2, because I am multiplying with 1 over x throughout. And look at that, 1 minus 0 instead of plus 0 over 2 is still a half. So indeed, they're squeezing the middle. So we can say, by the Sandwich Theorem, the limit of the middle function, which is then the x minus 4 sine x over 2x, definitely, because of the theorem, will also be equal to a half. Quite a nice problem. Lovely problem to start off with. And again, we started with the trigonometry section because that had the most complexities connected to it. Okay, our next one, we're going to bring in the log of base e, and to be even uglier, we're going to throw it in with a sine function. We're looking at the limit when x approaches 0 from the positive side of x squared, the sine of ln x. Now you need to understand why only from the positive, so let's quickly have a word about that. Ln x is log base e of x. The log of a negative number does not exist. You know that from school logs. Okay? Nothing has changed except at university we now work with ln x, which is log natural base e. So that just is said so that this does exist. Okay, no complexities again. We're going to start with the part that we know. So we're going to start off and say, you know what, the sine of ln x, we know, will be between 1 and -1, because this is in reality the sine of an angle. Okay? X is positive. So since x is approaching from the positive side, we know that this x squared will be bigger than 0. Always. It won't be equal to 0 because we're approaching the 0. Okay, so we know now. Why is that important? Remind yourself, because we're going to multiply x squared in, and there's inequations. We don't want negatives here. So we get minus x squared multiplied gives us negative x squared, which is now smaller than equal to x squared, the sine of ln x, and that in turn is smaller than equal to x squared. So what do we know? We know that these two functions will be squeezing the function that we want to take the limit of. So let's squeeze it. The limit when x approaches 0 from the positive of minus x squared is equal to 0. And that will definitely, it's a simple matter of just putting x equal to 0. That will definitely be the limit when x approaches 0 from the right-hand side or from the positive side of x squared will also be 0. So by the Sandwich Theorem, please folks write this out, by the Sandwich Theorem or the squeezing theorem, whatever you call it, the limit when x approaches 0 from the positive side of x squared, the sin of ln x will definitely be equal to 0, because the other two function squeezed it into that space. Okay, it seems very easy. I really hope you're understanding it so far. I'm going to make it one more. This is our last Sandwich Theorem problem, and I'm going to try and complicate it enough for you to think about what you learned about mathematics, the squares, the trig functions, and about fractions. Let's see what it says. It says the limit when x is approaching infinity again, and we're looking at the sine of 2x plus 7 multiplied by the cosine of x squared plus, look at this now, cos squared of 4 minus x cubed, and all of this is divided by the x. That's a mouthful. Now we need to decide, where do we start? Remember, x is going to infinity. So we can start by looking at, I would suggest, our product over here. Okay, so let's see. What do we know? We know that the sine of 2x plus 7 is definitely between 1 and -1. That we learned at school, and it's still true. We also learned that the cosine of the angle x squared here, remember that's just an angle. The x squared you don't think about now. Cosine of an angle lies between 1 and -1. Those are two facts that will never change. Okay? So what's going to happen if I multiply these two together? So in our product now, the sine of 2x plus 7 multiplied by the cosine of x squared, because they lie between those two limits, they would continue in the product to also lie between the two limits. Remember, you're not going to say -1 times -1 is a +1. You're looking at the sign of these things and what they will be based on what we know about them if we multiply the two together. These two limits will still remain the same. Okay, now that's very important for you to know. What else do we know? We know that the cosine of 4, now look, you'll notice I'm now zooming in on that component, that cosine lies between 1 and -1 as well. From school mathematics, that's where you've learned that. Okay, so what will happen if I square it? What happens to cosine squared 4 minus x cubed? Well, nothing happens at the top, but what will happen at the bottom is it will become a positive number. That is, we write a positive number here as bigger than naught. The bottom limit is positive, so it's bigger or equal to 0. Now, what am I going to do with that? I'm going to add it to this product. Now, it's a positive number, okay? So I can simply add it throughout without having to change signs on the sides. So that's my next one. I have naught, -1 remains, -1 for my bottom, okay, is less than equal to the sign. Remember, I'm adding this now, plus 7 multiplied by the cos of x squared plus the cosine squared of 4 minus x cubed. And that will now be less than equal to 2, the 1 plus the 1. The top limit here plus the top limit over there. So now I'm lying between -1 and between 2 over there. Okay, so what is squeezing my function will be determined once I've brought in my denominator. Look at how easy this becomes. This denominator is still, the x is positive, so I'm ensured that the signs won't change. So I have -1 over x is less than equal to, let's write it over x, the sine of 2x plus 7, multiplied by cosine x squared plus cosine squared of 4 minus x cubed. That's a mouthful, which is less than equal to 2 over x. And now we're going to squeeze. We're going to see what happens over there if x approaches infinity. And I can see that you're understanding this concept. I think it should be well understood now. If this bottom becomes very big, this becomes naught, that becomes naught. So the squeeze theorem will tell us that the thing in the middle becomes naught. So let's just say the limit when x approaches infinity of -1 over x will be 0. And that is the same as the limit when x approaches infinity of 2 over x. So by the Sandwich Theorem, the limit when x is approaching infinity of sine 2x plus 7 times cosine of x squared plus the cosine squared of 4 minus x cubed all over x will therefore also equal the value of naught. Okay, folks, so I hope that one made good sense to you. I'm going to look at a very important issue now, and this is another tool that you have in your maths toolbox. Remember, we looked at the form naught over naught a few video clips ago. If you forgot about that, go and look at that video again where we looked at the indeterminates. Now we're going to return to the indeterminates, but we're going to throw some trigonometry in, okay? And these will be questions where there's trig functions that are of the form naught over naught. Let's have a look. We're going to try and prove a tool that we're going to use. We're going to prove the limit when x is approaching 0 of sine x over x is indeed 1. Now, I've got a diagram here for us that we're going to use, but let's quickly just look at what I wrote here. If you make x naught, the sign of naught is naught, folks. The naught in the bottom makes it naught over naught. And yeah, what is the same here? Well, there's a x, there's a x, there's a x here, there's a x there. It's very important for you to notice this. Okay, so this is the tool that you're going to use to deal with forms naught over naught where trigonometry is involved. Well, let's see how we prove that function. I've got the diagram here for us. I'm saying O is the center of the sector A AOC with unit radius. So I've got a sector here, and I completed this quarter circle that has a unit radius, means the radius of this circle is 1. So this distance will also be 1 from O to C. Remember, a circle sector is like a piece of cake that you've cut. You cut the cake into sectors. Okay? So AOC is a circle sector. It has a unit radius, and BC is a tangent to this circle or to the sector. Now we know if something is a tangent, we can say that it is perpendicular to the radius, and here's the radius of 1. That's one of your grade 11 geometry theorems that you learned. That tangents are perpendicular to radii or diameters at the point where they make contact. Okay. Then the angle subtended by the arc AC is x. So that means this angle here is an angle x. Okay. Now, folks, to start proving this theorem, I need to decide. Remember, I need to decide on things that are squeezing what I'm going to work with. That's what I need to start with. So let's just look at what we've got here. Because this is a unit circle, the length of this side will be the sine of x. Why am I saying that? Well, let's just quickly bring a piece of paper in and show you that. Or let's do it underneath the diagram. If we have the following, we have O, this is x, this is O, the radius is 1, and that's perpendicular, that's A, and then I've created the D. So I drop from A, I drop an altitude D onto this radius. So you can immediately see these two lines are parallel if we need them. Okay, but the point is, I want to take the sine of x. The sine of x will be the opposite over the hypotenuse, AD over 1. And because the hypotenuse is 1, AD is equal to sine x. Okay, so I can write that onto the side AD. And in the same way, I have the tan of x being something related to BC. Let's quickly see how that happened. If I have this triangle again, I'm working on the outside now, OC. OC is 1. Okay, and B is up there. If I take the tan of this angle x, the tan of x is BC divided by 1. I'm working in a unit circle. So the line BC has a length equivalent to the tan of x. So this here will be tan of x. And you'll see why that's important now. So now I'm going to choose very strategically to squeeze. I need to squeeze. My bottom, I'm going to start working with areas. My lower function that I'm going to work with, I'm going to start saying the area of this triangle AOD can be smaller or equal to the area of this sector. The area of sector, let me just put in there triangle, the area of sector AOC, that's this one, the piece of cake, and that area is smaller than the big area of triangle BOC. Okay, I've stated my limits, and now let's see where this goes. Okay, Vitsies, now we have to remind ourselves of two very important things. How do we find the area of a triangle, and how do we find the area of a circle sector? By now you should have worked with that, so I'm just going to remind you by applying it and telling you slowly what I'm doing. Okay, first of all, we're looking at the area of this triangle AOD. Now that will be half base. Now my base is OD. Now remember what we said earlier, how this became sine. This will be the cosine of this angle x, this length. By the same token, the cosine of x is adjacent over hypotenuse. Okay, so if I write that down, the cosine of x is adjacent, OD over hypotenuse 1. So OD is indeed cos x. Okay. Now, the bottom will then be a half base. Now, the base is cos x, and the height we calculated to be sin x. Okay, that's a normal area formula. Let's go and let's finish the area on the outside here as well, because it's another triangle. Area of triangle will be half base times height. But now look at how strategically clever I'm going to be. I'm going to use this as my base because I know the height, O to C, is 1. It's a unit circle. So this again is half base, and the base is tan x multiplied by the 1. Okay, so it stays half tan x. Now remember yourself, the area of a sector, folks, is a half the radius squared of that sector, which we know is 1, multiplied by the angle that is subtended at the center of the sector. And at the center of the sector is the angle x. So we can immediately write this as a half. Radius squared is 1, so I'm not even going to waste time. Now let's do it, just to remind ourselves. It's 1 squared. The angle subtended at the center will definitely then be an x. Now I'm going to do some cleaning up before I continue. On each one of these sides there's a half. So I'm just going to throw it out, because if that was a 2, a 2, and a 2, I would do exactly the same thing. Okay, so it simplifies things a little bit. Now look at what I want to form. I want to form the sine of x over x. So in the middle here, I've got the x. I need to bring in the sine of x. So how do I bring that in? I'm going to multiply each one of these sides with 1 over the sine of x, so that indeed I can start forming this. Let's do that. Here, if I multiply with 1 over sine, the sines remove themselves, and I'm left with a cosine of x. Okay? Then 1 squared is 1. X times 1 over the sine of x is x over the sine of x. Okay, it's there. It's just the other way around. And on this side, I'll have, let's change tan to the sine of x over the cos of x, and I'm multiplying it with 1 over the sine of x. So you can see those two are going to remove one another. So what am I going to be stuck with at this point? I'm going to have cos x that is small and equal to x over the sine of x, and that there in turn is smaller and equal to 1 over the cosine of x. Okay, so here I'm working in my first quadrant. Very important to notice that I'm in the first quadrant. So the value of the angle that's subtended here lies between 0, remember you're working in radians, 0 to pi over 2 radians. Pi over 2 radians, just to remind you, is equivalent to 90 degrees, don't forget. Okay, so I know now that and this is becoming important because I'm going to now try and form sine x over x. I've got x over sine x. So I need to acknowledge that pi, or that the angle at the center, lies between 0 and 1. Not equal to, strictly between. It can't be equal to, because then I don't have a triangle. I have a line that lies on OC. So it's important to not put your equals here, because then you will not be doing the right thing. So which is in quadrant 1. Okay, and in quadrant 1 we know everything is positive. Okay, so it's very, very safe for us to turn these things around. But now I'm going to turn them around, and then we're going to discuss what's going to happen next. So that becomes sine x over x, and this becomes cos x. The moment you reciprocate these two, remember they're positive. Now look at what I'm going to write here on the side. 2 is definitely smaller than 3. Okay? But if I turn them around, a half is going to be bigger than a third. And we know that. Okay? So the moment I reciprocate the positives, the signs will also change. So this is very, very key for you to remember, that instead of facing this direction, it now becomes that. So what do I have? I have a squeeze here by the two functions cos of x and the cos 1 over the cos of x. So now I can apply what? My pinching theorem. I'm looking at the limit at naught. So I'm saying the limit when x approaches 0 of 1 over cos x. Now I know x is in a denominator, but it's connected to the ratio cosine. And if you remind yourself, your cosine graph starts at 1 and then goes to a minimum value of -1 and continues in that way. So this is naught, and the cosine of naught will be 1. So if I make this 0, I got 1 over the cos of naught, which is 1, so my result is 1. And let's look at what happens there. The limit when x approaches 0 of the cosine of x, well, the cosine of x is 1. So this still stays 1. So the two functions that squeeze, the middle is going to 1. So by the squeezing theorem or the sandwich theorem, the limit where x approaches 0 of sine x over x will definitely also be 1. Okay, Vitsi, so we just learned something very important. We learned how to deal with an indeterminate naught over naught where trigonometry is involved. Okay, so let's write it down. The limit where x is approaching 0 of sine x over x will always be 1. Why is that the case? If we put the naught in, the sign of naught is naught. X becomes naught, it's 0. So this here, folks, is a tool for you to work with this indeterminate quantity when there's trigonometry involved. Let's look at an example and see how it plays out. Let's look at the limit where x approaches 0 of the sine of 4x divided by, let's make it a bit trickier, the sine of 3x. Okay, now remember I want to form this. And just by the way here, folks, let me show you something new. The limit where x is approaching x over the sine of x, we are turning it back on its head, will still be 1. Because if you turn 1 around, it's still 1. So this principle applies to both of those. And even beyond that, if I have the limit where x is approaching 0 of the sine of 20x, then in the bottom of this 20x, sine of 20x, I must have 20x. So the important part is that that is the same. It doesn't have to be the same here. Okay, so this will be equal to the limit where x approaches the sine of x over 2, as long as I have an x over 2 at the bottom. All of these are going to give you 1s. Okay, so as long as that and this is the same, or this and what's in the denominator is the same, that's the key thing here to remember, because it's going to determine what we're going to do with the 4x and the 3x that's currently in the problem that we're looking at. Okay, so let's see, how do we deal with this? Well, I need to bring in a 3x, so I bring it in. Okay, why? How do I bring it in? Because by multiplying with a 3x. Why am I doing it? Because if I put my finger, if I put the pen on that, well, there's a shadow there. So if I ignore the top, I get 3x over the sine of 3x. And I need to do the same. I need to divide by a 4x so that I form this situation over here. Okay, so let's see if we put them together, if we change the value. It's very important. We're adding things here. So if we add things by multiplication or division or addition, subtraction, we need to undo it because it wasn't there in the beginning. That's the important part. Okay, so I'm writing that deliberately on top of each other so that it looks like that. And then this was in the bottom and it's multiplied. So sine of 3x is still in the denominator with its 3x that I brought in. So I brought in a 4x and a 3x. 3x at the top, the 4x at the bottom. Well, if I look carefully, the x's will cancel, but the 3 over 4 is not going to cancel. So I must still multiply with 4 over 3 so that I undo the 3 over 4. It's deliberate. What I'm doing is a deliberate attempt at creating things that looks like my tool that gets rid of this indeterminate. Okay, so the times 4 over 3 tags along. Now I'm ready. I formed these things. Okay, the limit when x approaches 0, it takes on this form, is 1. So that is 1. I'm dropping the notation. Multiplied by the limit when x approaches 0 of the second part, which is similar to that, which is also 1. Okay, and then multiplied by this, just doesn't change, it tags along. So my limit will be 4 over 3. Now remember, what did I apply here? I applied one of the rules of my limits, which you know, you've learned them quite a while back in class. You've learned about those rules. Okay, so if I take the limit when x approaches a of fx times gx, it's the same as taking the limits separately and multiplying them. And that's exactly what I did over here. Okay, so again, this is the important part. This is very important to remind yourself of constantly, that those two things must be the same for this to apply. So I'm saying to you, if this was 20x over x, sorry, it wasn't equal to 1 anymore. Okay, let's look at one last one, and this one is going to be a trigonometric one where we use cosine. So let's look at the limit where x is approaching pi over 4 radians of the cosine of 2x divided by the sine of x minus the cosine of x. And let's see what we can do with that. Okay, let's have a look. At school, very, very, very important. You learned about the double angle idea. Nothing has changed. So for the cosine of 2x, I have 3 options. I have cosine squared x minus sine squared x, or I have, if you make this into 1 minus cosine, I have 2 cosine squared x minus 1, or if you change the cosine to sine, 1 minus 2 sine squared x. And remember the tool that I'm going to use. Okay? So I'm trying to, if you put pi over 4 in here, let's just see if the form matches up. Pi over 4 times 2 is pi over 2. The cosine of pi over 2 is definitely 0. Your cosine graph, remember, goes to pi over 2 here, starts at 1, and that cosine is 0. So that is 0. The sine of pi over 4 is 1 over root 2 minus the cosine of pi over 4 is also 1 over root 2. So indeed we have a form of 0 over 0. So we need to create our options of how do we get rid of this. Now let's have a look. If we now choose one of the 3, and I think I'm going to choose the one that's going to be the easiest to form, which is the first one. I need to bring in the sine function so that I can work with it. So I'm going to say this is the limit x approaches minus pi over 4. But now remember, if you look at these two factorized, cos squared x minus sine squared x is cos x minus sine x times cos x plus sine x. That is your difference of squares. Now I've got it in the denominator, but the wrong way around. Now you learned again that if you want those two to turn, we need to remove a negative. If we remove the negative 1, then this is sine x minus cos x multiplied by the second bracket. Okay, so that bracket just comes down and multiplies. So I'm going to do that. I'm going to say this is minus the cosine of 2x divided by the sine of x minus the cos of x. I turned it around, and now I need to bring the second part in. So I need to times this with cos x plus sine x. Why am I doing it? To form the cos of 2x, and I get rid of the 0. But what I multiply the denominator with, I have to multiply the numerator with. So I'm multiplying with 1, and it doesn't change the value of what I had in the beginning. Okay, let's see what this produces for us. The limit when x approaches the pi over 4, the negative I can remove. I have the cos of 2x multiplied by the cos of x plus the sine of x. Now, folks, you'll notice I'm not multiplying this out because I know what I did here. I deliberately did this so that I can form cos 2x. If I multiply this out, a minus b, a plus b, it's the difference of squares. It becomes the cos squared of x minus the sine squared of x. Okay, so let's see what happened from here now to what I had at the top. I took out my negative, and I was supposed to swap those two around. So those is, in fact, I'm just going to fix it on here. That's a cos minus a sine of x. That happens when you talk so much. Okay, so if I remove that negative, the purpose was to swap them around to create that. Okay, so I have the limit. I'm 2 steps away from getting to my result. This here is cos 2x by my theory that I learned earlier. So that removes the denominator in its entirety because the denominator is equal to the cos of 2x. The negative tags along, and you know what? I'm going to put it in front of the limit because of my law that says the limit when x approaches a of k times the function f of x is the same as k times the limit when x approaches a of f of x. You guys must go and remind yourselves of these rules of limits. Okay, now I'm ready to take the cos of x plus the sine of x. Okay, I know the minus 1 stays out. I bracket, drop the notation, the cosine of pi over 4 plus the sine of pi over 4. Now these are both special angles, so I have minus 1 over the root of 2 plus 1 over the root of 2. If you punch that into your calculator, you'll see that the sine of pi over 4 and the cosine of pi over 4 is exactly the same thing. So there's 2 of those. I multiply the negative in, so it's minus 2 over the root of 2. And if you want to clean that up, you can write it as minus the root of 2. Okay, punch it into your calculator, check that that is indeed the case. Why is it the case? Let's quickly talk about that to make it easier on you. What is 2? 2 is equivalent to root 2 times root 2. Okay, and in the denominator I have a root 2, so root 2 cancels, so 2 over root 2 is the same as root 2. Okay, folks, work slowly. You saw that even doctors of maths makes mistakes, or maths education makes mistakes. Be very careful. Don't make sign errors. Don't cancel things that you can't over terms. Don't take roots. All of that stuff could cause problems for you when you do these type of complicated questions. So the 4x and the 4x don't cancel to 1 and 1 because it's the sine of 4x over 4x. You can't touch the two 4x's. Your tool you learnt about was the indeterminate 0 over 0 when trig is involved, and the tool said the limit when x approaches 0 of the sine of x over x is 1. Now it doesn't have to be the sine of x, let's remind ourselves. It can be the sine of 20x over 20x. The key is that whatever is there must be over here. Whatever's there must be the same over there. And if it's not there, we bring it in. Okay, that then concludes our applications of the sandwich theorem and what we've learned about the sandwich theorem for the day. Thanks for watching.